Every useful program you will ever write needs to remember things. Think about it. If your program can only do something like 2 plus 2, how does it hold on to that for later? How does it remember a user's name, or a product's price, or the current score in a game? Without a way to store and retrieve data, your program is just a calculator that forgets everything the moment it finishes one operation. This is where variables come in. They are the fundamental mechanism for giving names to tiny, individual cells of memory, allowing your program to store state, build upon previous results, and interact with the world in a meaningful way. Today, we are going to unlock exactly how C++ lets you manage these memory locations, giving you precise control over your program's data. By the end of this lesson, you will be able to differentiate between a variable's declaration and its definition, understanding the critical one-definition rule. You will identify the purpose and memory implications of C++'s fundamental integer, character, and floating point types, knowing when to use each one effectively. You will also correctly use literal suffixes like f or l and digit separators for type precision and readability. Finally, you will distinguish between Lvalues and Rvalues in expressions, which is a concept that becomes absolutely critical for advanced C++ features like move semantics. Let us dive in. When I first started, I thought of a variable as a sticky note. You write age on the note and 30 on the wall behind it. But that is not quite right for C++. Think of a variable more like a labeled container, a specific box in your computer's memory. You give it a name, say user age, and then you put a value, like 30, inside that box. The type of the variable, like int for integer, dictates the size and shape of the box and what kind of stuff you can put into it. So, formally, a variable is a named storage location in memory that holds a value of a specific type. That type is crucial. It determines how many bytes of memory are allocated for that variable, the range of values it can hold, and what operations you can perform on it. An int variable, for instance, might occupy 4 bytes on your system, allowing it to store integers typically from -2 billion to +2 billion. Now, here's where it gets interesting. C++ distinguishes between declaring a variable and defining it. A declaration simply introduces the variable's name and type into the current scope. It tells the compiler, hey, there is a variable named x of type int somewhere. A definition, however, is where the actual memory allocation happens. It is where the compiler reserves those 4 bytes for x. Most of the time, when you write something like int count equals 0, you are doing both, declaring count and defining it, allocating its storage, and initializing it to 0. But you can declare a variable without defining it, using the extern keyword. This is common when a variable is defined in one source file, but used in another. For example, extern int global counter declares global counter, but does not allocate memory for it here. The definition, int global counter equals 100, must exist exactly once in another translation unit. Let us look at a concrete example. I will declare and define a few variables. This first line, int score equals 100, both declares an integer variable named score and defines it, allocating memory and setting its initial value to 100. The next line, double pi equals 3.14159, does the same for a double precision floating point number. Then, extern int game level is a declaration only. It tells the compiler that game level exists as an integer somewhere else. If I then try to print score and pi, the program will compile and run. When you execute this, you will see score, 100, and pi, 3.14159, printed to the console. Now, what happens if you forget to define game level somewhere? If you try to use game level without a definition, the compiler will be fine, but the linker will throw an error like undefined reference to game level. The linker cannot find the actual memory location for that variable. This is a classic linker error, not a compiler error, because the compiler saw the extern declaration and assumed the definition would be found later. The most common mistake, and one that will trip you up, is violating the one definition rule, or ODR. This rule states that every variable must be defined exactly once across all translation units that make up your program. You can declare it multiple times, but only one definition is allowed. If you define the same variable twice, even in different files, the linker will complain. Imagine you have int counter equals 0 in file 1.cpp and int counter equals 0, again in file 2.cpp. When the linker tries to combine these, it sees two separate memory allocations for counter and does not know which one to use. You will get a linker error similar to multiple definition of counter. This is why extern is so important for global variables shared across files. Now that you understand how variables are named memory locations, let us talk about the types of data those locations can hold. Think of these fundamental types as different sized and shaped containers. You would not try to store a gallon of milk in a thimble, nor would you use a huge barrel for a single grain of rice. C++ gives you specific types for specific data needs. C++ provides a set of built-in fundamental types. For logical values, we have bool, which holds either true or false. It typically occupies 1 byte, though the standard allows for flexibility. For single characters, there is char, also typically 1 byte, storing an ASCII character like A or Z. C++20 introduced char 8t for UTF-8 characters, and we also have wchar-t, char 16t, and char 32t for wider character sets. For whole numbers, we have integer types, short, int, long, and long. Their exact sizes are platform-dependent, but the standard guarantees minimum ranges. For example, int is usually 4 bytes on modern 64-bit systems, providing a range of roughly plus or minus 2 billion. Each of these can also be signed, default, allowing negative values, or unsigned, only positive values, doubling the positive range. You should use int for most general-purpose integer needs. For numbers with decimal points, we have floating point types, float for single precision, double for double precision, and long double for extended precision. Double is the default for floating point literals and computations due to its balance of precision and performance. Finally, void represents the absence of a type, primarily used for functions that return nothing or as a generic pointer type, void pointer. If you need integers of a precise size, which is critical for portable code or interacting with hardware, you should include the C standard int header. This gives you aliases like standard int 32t for a guaranteed 32-bit signed integer, or standard uint 64t for a guaranteed 64-bit and signed integer. This avoids the platform-dependent sizes of int or long. Let us declare some variables using these fundamental types. Here, bool is ready equals true, creates a Boolean variable. Char grade equals A, stores a single character. Int population equals 8 million, uses a standard integer. Notice how long world population equals 8 billion LL, uses a long for a larger number and a digit separator for readability. The LL suffix explicitly makes it a long literal. For floating point, float temperature equals 25.5 F, uses F to specify it as a float. Without it, 25.5 would be a double literal. Double gravity equals 9.80665, uses the default double. And for precise sizes, standard int 16t sensor value equals negative 1024, ensures a 16-bit integer. When you print these, you get their respective values. Ready, 1, grade, population, 8 million, world population, 8 billion, temperature, 25.5, gravity, 9.80665, sensor value, negative 1024. A common mistake is integer overflow. If you declare short s equals 32,767 and then try s equals s plus 1, a 16-bit signed short cannot hold 32,768. It will wrap around to negative 32,768, which is a silent error that can lead to extremely hard to debug issues. The compiler will not warn you about this by default. Always consider the range of your chosen type. Another one is implicit type conversion. If you write float result equals 10 divided by 3, you might expect 3.33. But 10 divided by 3 are both integers, so integer division occurs, resulting in 3. This 3 is then implicitly converted to 3.0f and assigned to result. To get the floating point division, you need float result equals 10.0f divided by 3.0f, or float result equals static cast float 10 divided by 3. Now that you know about fundamental types, let us talk about how you write specific values directly into your code. These are called literals. Think of them as the raw data you hardcode. For example, 42 is an integer literal. 3.14 is a floating point literal, but C++ offers more precision and readability options for these. Integer literals can be decimal, like 10, octal, prefixed with 0, like 012, which is 10 in decimal, hexadecimal, prefixed with 0x, like 0xa, which is 10 in decimal, or binary, prefixed with 0b, since C++ 14, like 0b1010, which is also 10 in decimal. For readability, especially with large numbers, C++ 14 introduced digit separators, the single quote character, like 1 million. Floating point literals are double by default, like 3.14. To specify a float, you append f or f, as in 3.14f. For long double, you use l or l, like 3.14l. Character literals are single quotes, like a, and string literals are double quotes, like hello. C++ 20 also added U8 prefix for UTF-8 string literals, like U8 high. Here is an example of various literals. Int decimal equals 42 is a standard decimal. Int hex equals 0x2a is hexadecimal, also 42. Int binary equals 0b101010 is binary, again 42. Notice long big number equals 1,234,567,890 LL, using digit separators and the LL suffix for a long. Float precise float equals 1.234567f, explicitly uses f. Without it, 1.234567 would be a double. Char symbol equals U8 copyright symbol, uses a UTF-8 character literal for the copyright symbol. When you print these, you get decimal, 42, hex, 42, binary, 42, big number, 1,234,567,890, precise float, 1.234567, symbol, copyright symbol. The most common mistake with literals is forgetting the suffix for floating point types. If you write float my float equals 3.14, the literal 3.14 is a double. The compiler then performs an implicit conversion from double to float, which can lead to a loss of precision if the double value cannot be exactly represented by a float. For example, 3.14159265535 as a double will be truncated when assigned to a float, resulting in 3.1415927 on most systems. Always use f for float literals. Now that we have covered variables and their types, let us talk about a more subtle but crucial concept, Lvalues and Rvalues. This distinction becomes incredibly important when you get into more advanced C++ features like move semantics, but the basics are simple. Think of an Lvalue as something that has a persistent memory address, something you can take the address of. An Rvalue is a temporary value, something that exists only for the duration of an expression. The L in Lvalue historically stood for left-hand side of an assignment, meaning you can assign to it. The R in Rvalue stood for right-hand side. So, int x equals 10 means x is an Lvalue because it refers to a specific memory location, and 10 is an Rvalue because it is a temporary literal value. You can assign to x, but you cannot assign to 10. Let us look at some examples. In int a equals 5, a is an Lvalue, and 5 is an Rvalue. In int b equals a plus 3, b is an Lvalue. A is also an Lvalue, but the expression a plus 3 evaluates to a temporary value, which is an Rvalue. You can assign a plus 3 to b, but you cannot assign something to a plus 3. Here, int x equals 10 makes x an Lvalue. Int y equals 20 makes y an Lvalue. The expression x plus y evaluates to a temporary integer, which is an Rvalue. If I try to print x, y, and x plus y, I get x, 10, y, 20, x plus y, 30. The most common mistake is trying to assign a value to an Rvalue. For example, if you write 10 equals x, the compiler will immediately give you an error like, error, expression is not assignable. You cannot change the value of the literal 10. Similarly, if you try x plus y equals 50, you will get the same error. Error, expression is not assignable. The result of x plus y is a temporary. It does not have a persistent memory location you can assign to. Understanding this distinction is crucial. An Lvalue refers to an object with an identifiable address, something that lives somewhere. An Rvalue is a temporary, a literal, or the result of an expression that does not persist beyond that expression. This concept will be foundational when we discuss references and move semantics later on. You now understand three critical aspects of C++ programming. First, you can differentiate between variable declaration and definition, and you know the importance of the one definition rule to avoid linker errors. Second, you can identify the purpose and memory implications of C++'s fundamental types, from bool to double, and know when to use standard int 32t for precise sizing. Third, you can correctly use literal suffixes and digit separators for precision and readability, and you can distinguish between Lvalues and Rvalues, avoiding common assignment errors. Next time, we get our hands dirty with the actual building blocks of every program, literals and initialization techniques.